Hi everyone. So far we've been studying models for a single random variable, continuous or discrete. Many problems in statistics involve models where we have several random variables simultaneously, and we might be interested in looking at what happens when one of them changes. Are these two variables independent or dependent from each other? Some things that we've been discussing. So in this video, I want to walk through some situations where we might have two different random variables involved in an experiment. So let's say, for example, to get this ball rolling, we are an insurance company and we write insurance, different types of insurance. So homeowners, automobile insurance, these would probably be the two most common lines of insurance. And many insurance companies offer discounts if you take out both a homeowner's and auto insurance policy. So if you bundle your insurance, they'll give you some discount. So they may have some customers that have both auto and homeowners insurance. So what we are considering here is, okay, what happens if we were to pick one of their customers that has both an auto and a homeowner's insurance policy, and random variable A is going to denote how much their auto deductible is. So they might have an automobile deductible of $100 or an automobile deductible of $250. And if you're not familiar with how deductibles work in insurance, if I have an auto insurance policy, for example, with a $100 deductible, I get in an accident and the damage is $500. This means I'm responsible for paying the deductible, which is $100. The insurance company would cover the rest of the damages, which in this case would be $400. Okay, so on this table, let's make sure we're reading the table correctly. For each of these rows, we have information about what happens if for auto insurance policies of $100 deductibles, auto insurance policies that have $250 deductible. So this company, their auto insurance policies have one of two options, a $100 deductible or a $250 deductible. And for homeowners insurance, they have three options. Either you can choose to have no deductible, you can pay a $100 deductible, or a customer can choose a policy that has a $200 deductible. And so over here, we have what we've been calling a two-way table or a contingency table. And this table, rather than giving counts of out of 1 million customers, if they were a huge company, how many of their customers have this type of insurance, instead we're describing things in terms of proportions. So for example, if I want to interpret what this entry means right here, this is telling us the probability that when A is equal to 100 and H is equal to 0, that the proportion of all of their customers that have a $100 auto deductible and at the same time have a homeowner's insurance policy with $0, this should be 20% of all of their customers. So in other words, this is telling us 20% of all of their customers have joint policies with an automobile deductible that's $100 and a homeowner's deductible, which is $0. So they have no homeowner's deductible. So each of these entries inside the table is an and probability. It's telling us the probability that two things happen at the same time. In this case, a randomly selected person's policies have an auto deductible of 100 and a homeowner's deductible of 0. This 0.1 over here would tell us that 10% of all of their customers have a $100 automobile deductible and $100 homeowner's deductible, and so on. So it's important that when you're reading these values inside the table, these are and probabilities, the probability that two events occur at the same time. Let's consider another natural question that we might want to ask, which is, what is the probability that a randomly selected customer that has both of these policies has an automobile insurance policy with a $250 deductible? And notice here, we have no condition on what their homeowner's deductible should be. So what we would do is essentially want to calculate the total in the row corresponding to A's 250. So we're going to add up what are all of the possible ways that you could have a 250 automobile deductible. Well, we could have a $250 automobile deductible and no homeowners deductible, so that's 5% or 0.05. We would want to add to that as well the people that have a $250 auto deductible and a $100 homeowners deductible, so that's another 15%. So we would add another 0.15, and then the last possibility would be corresponding to this entry over here, which is the 250 automobile deductible and the $200 homeowners deductible. And so we see that this all adds up to 0.5. So that would be the equivalent of how we would calculate the total row over there. So this is telling us that 50% of their customers that have both auto and homeowners insurance, 50% of these customers have an automobile insurance policy that has a $250 deductible. And that takes into account all of the people, regardless of what their homeowner's insurance deductible is. So we add those all together. So we still can calculate probabilities of how likely it is that one random variable has a certain value, which is what we just did here. And we could similarly ask the question, what is the probability that a randomly selected person with both of these policies has a homeowner's insurance policy of $100? And that would mean we're just focusing on this column in the table for when H is equal to 100. And to calculate what is the probability that H is exactly equal to 100, we would do the same exercise, which is we would add up all of the probabilities in the column corresponding to H equals 100. So we would take into account that we've got 10%, 0.1 for people that have homeowners of 100 and auto of 100. And then we have another 15% or 0.15 of homeowners with a $100 deductible, but took the other option of a $250 auto deductible. And so altogether, that adds up to 0.25. And we can interpret this as saying 25% of their customers that have both homeowners and auto insurance have a homeowner's deductible equal to $100. Okay, so with that previous insurance example in mind, let's define a couple of terms more generally. So if I have two discrete random variables that we'll denote with x and y, then we can define what's called the joint probability mass function, which we typically might give a p. Sometimes you might use f. So the letter here is kind of not that important, but we'll use p since it's representing a probability. So we'll say that this function depends on both x and y. So it's a function of two variables. And this function tells us if I evaluate it at specific values of x and y, then this tells us what is the probability that variable x is equal to a and random variable y is equal to b. So that's like reading the inside cells of that table. Those were intersections. We can still think about each of these random variables independently, or at least separately from the other. So when we do this, we can construct what's called a marginal probability mass function of x, or we could do this for the random variable y. And so if I just focus on finding the marginal probability mass function of x, then what we need to do is now we're going to get just a function of x. So this is going to tell us if random variable x is equal to this specific value, what is the probability that that would happen? So in the end, what we get is a function of just random variable x. In the way that we construct that function is by summing over all of the possible values of random variable y. So in other words, this is saying we're going to calculate the totals corresponding to x. And we can do the same for random variable y. We can calculate a marginal probability mass function for y, which is just going to tell us if random variable y equals a certain value, what is the probability that that would happen. So here we get these probabilities by summing over all of the possible values of x for each separate value of random variable y. So that's a mouthful, and I think what's the easiest way to define these and make sure that we understand what these definitions are is to walk through an example. And so let's stick with this insurance example. So again, we've got two possibilities for auto insurance deductibles, $100 and $250. Three possibilities for homeowners insurance, that's $0, $100, $200. And so if we want to find the probability, the marginal probability mass function for random variable A, well then what we'd want to do, if we use this definition, we are going to sum over the values of H. So for example, when A is equal to 100, we sum over all of the values of H. So we're going to take the 0.2 plus the 0.1 plus the 0.2, and that gives us 0.5. So this tells me if I want to find this function in the end, the values are going to be piecewise functions. Remember, when we were expressing discrete random variables, their probability distributions, we typically do this if we don't have a million possibilities using a piecewise function. So I can say this is going to equal to 0.5 when random variable A is equal to 100. Then we've got another possibility that we need to consider, and that is what happens when A is equal to 250. And for that, we could add up these probabilities, and it just so happens that this gives me 50% as well. There's no reason why they don't have to always be the same. They're most of the time going to be quite different, and then we might have other values of A that we still need to sum over. But this exhausts it all. So if A is equal to any other value other than 100 or $250, then the probability that someone has an auto insurance policy with a deductible other than $100 or $250 would be impossible, would be 0. So this would be a way that we can express this marginal probability mass function for A as a piecewise function. And you can imagine what it would look like if we wanted to do the same thing for random variable H. And this is what I'm going to ask you to do with a slightly different table on the reading assignment. And lastly, before we go, I just want to motivate some of the work we'll be doing in class. So there is a mirror image to this with continuous random variables. And I want to just define those terms on the last slide. And so if we're in the case where x and y are two continuous random variables, then we similarly would want to consider, well, how likely is it that this experiment has a value of x that is between certain values and a value of y that falls between certain values? So we can still use this joint probability. Now we call it a density function because they're continuous random variables to calculate and probability. So we're calculating the probability that x falls between certain values and y falls between certain values. And similar to how we worked with PDFs before, this means we're going to need to integrate over certain range of values for x and y. So we've got double integrals that we're going to have to work on in class. So if it's been a while since you've set up and evaluated double integrals, it might be nice to practice that or just look at that ahead of time. And I put some review materials up in Canvas if you want to go back and get some extra practice in double integrals. I think all of us can use some extra practice in double integrals with double integration. And if we want to calculate the marginal probability density function, say for one of those random variables, then instead of summing over all of the possible values for the other random variable, we don't sum with continuous random variables, we integrate. So we're going to integrate over y. So keep in mind when you do this, that y is our variable here. And so when we integrate, we treat y as a variable. So this is like a single integral with y as the variable. And therefore, when we do this integration, we should be treating x as a constant. And what we get out in the end, since we're integrating over y, should be just a function that depends on just the value of x. And same idea, if we wanted to do a marginal probability density function for random variable y, now we just change what we're integrating over. So now we integrate over x. And in this case, we would then treat y as the constant when we do that integration. And so in the end, the result will be a function that depends on just the value of random variable y. So we'll work with these in class, since I imagine going through some double integrals might be useful as well. And so just to see an example, we'll pick up in class of where we might have a continuous random variable is we can consider the following scenario where you're a pharmacy, and in this pharmacy, we have a drive-up window for customers that don't want to come in the store, and there's a walk-up window for customers that are in the store. And sometimes the drive-up window is in use, other times no one's in the drive-up window. So X is denoting what proportion of time during the day was somebody at the drive-up window, and Y is denoting what proportion of the day was someone at the walk-up window. And so then we can calculate things like, well, what is the probability that the walk-up window was in use 50% of the day or less, and that the drive-up window was in use more than 50% of the day, or other such questions. And so in this case, the joint probability density function, the joint PDF, is not a table because x and y are a continuous range of values, each of them between 0, meaning that window was not in use at all during the day, up to a value of 1, which would tell us that that window was in use the entire day, 100% of the day. But what you want to be careful about is when we're reading a joint PDF for continuous random variables and we want to calculate probabilities, we don't evaluate this function at certain values of x and y. Rather, we need to set up and evaluate double integrals to calculate probabilities. And if I want to answer questions that are just related to random variable x, so like how likely is it that the drive-up window is in use from 25% to 50% of the day, ignoring y at all, well, that's where we would want to consider looking at just a marginal probability density function for x. And if we wanted to ask questions like how likely is it that the walk-up window is in use for a certain proportion of the day, ignoring x entirely, well, that's where the marginal probability density function of y would come in handy. So I'll do some work with both the continuous and discrete joint probability distributions in class. Be sure to take a look at the quiz before coming to class, and we'll dive deeper into these concepts together.